Let's start. So very good evening to all of you. The last class, sixth lecture we were having it. So just a moment. So last class, what we have discussed is regarding phosphorus 13 NMR as well as tin 119 NMR. I think we have discussed in detail regarding the 119 tin NMR. So we got information regarding the side bands, etc. So then you calculate the anisotropy. The coupling constant also I have mentioned two types of coupling constant. One is because of the magnetic inequivalence. So they are chemically same, they are magnetically equivalent. One is tin 117, another is tin 119. Then we discuss something regarding how the environment changes, the line shape changes, how the tin NMR from S and O is different from SNO2. There is a large difference between the tin NMR of SNO and SNO2. This has been explained based on the lone pair of electrons. You can see from this slide. These things we have discussed in detail. And one representative complex also I have mentioned. Wherein tin exists in two different configurations. Configuration means coordination environments. Correct? Na? So these things we have discussed in the last class. And towards the end of the class, we discussed how to suppress sidebands. Although sidebands can give some information, this will be a problem when you have multiple sites. For example, in proteins and there are multiple carbon sites, and it will be difficult to get information, which is difficult to find out which is isotropic peak and which is the sideband. So there is a program called sideband suppression, and in that we use rotor synchronized 180-degree pulses, and these pulses will average the sideband, and you will get a negligible sideband. This you can see from this spectrum that the sideband suppression can be effective. And then we have calculated also components of the chemical shift anisotropy. So chemical shift anisotropy is significantly higher for as prepared sample or low temperature heated sample, as can be seen from the line width. And as you increase the temperature, the lines become more and more sharper. Why this happens? Because there is an order. As you increase the temperature, ordering develops. The fixed bond lengths and bond angles gets a fixed number, and that is why we get sharp peaks, because the star peak is characteristic of the long range ordering. Now let us go to lecture 7. Before giving the more in detail regarding the NMR of other nucleus, let us mention something regarding the dipole-dipole interaction and the chemical shift anisotropy. We have been telling this over the last 6 lectures. I've been always telling that dipole-dipole coupling is having 3 cos squared theta minus 1. Then chemical shift anisotropy is also having a 3 cos squared theta minus 1. But probably I have never told how they depend on the applied magnetic field. So in market, you have NMR machines having a variety of magnetic field, is it not? So as you increase the magnetic field, the resolution increases. For example, if you run an NMR with a 300 megahertz NMR machine, and if you run an NMR with a 500 NMR machine, 500 megahertz NMR machine, you will have a different resolution. 500 will be having a more resolution, and 300 will be having a less resolution. So this resolution depends upon the magnetic field, applied magnetic field. But what is the dependence of dipole-dipole coupling on the magnetic field? Can I reduce or can I increase this dipole-dipole coupling constant by varying the magnetic field? Suppose I have a 300 megahertz machine and a 500 megahertz machine and a 900 megahertz machine in the same lab. Can we reduce the dipole-dipole coupling by varying this, by recording the spectrum under different magnetic fields? The answer is no. Because you see the dipole-dipole coupling, if you see the classical level, it is nothing but two magnets I and K or J and K. Correct? Na? So this is the K is the nucleus, and you can see the electron cloud is there. So this is nothing. If you see a magnet, it is like this interaction between J and K or interaction between J and K. K here, J here, K here, J here. So this is nothing but the dipole-dipole interaction. In classical equations are available. The dipole-dipole coupling is expressed by this type of relation. Dipole-dipole coupling is between the J and K is expressed by a distance, by an expression like this. Here, gamma J and gamma K corresponds to gyromagnetic ratios of J nucleus and K nucleus. So there is no magnetic field coming into picture. You see here in the coupling, the dipole strength of coupling or the coupling constant can be expressed by this relation. And here only constants are there. The only variable is nothing but the distance between J and K. Distance between J and K. In fact, the distance increases, the RJD or the coupling constant decreases, the strength of coupling, dipole-dipole coupling decreases with increase in distance. In fact, it is inversely proportional to the cube of the distance. So what I want to convey from here is that whatever may be the magnetic field you apply, dipole-dipole interaction does not change. It remains like that. That is why we call as it is independent of the applied magnetic field. Now what happened to chemical shift and isotropy? Because these are the two contributions made to the line width of NMR pattern or broadening of the solid state NMR pattern. If you see the expression here, the magnetic field felt at the local site, that is called B loc, is nothing but the magnetic field felt at the local site is nothing but 1 minus sigma into B0. So what happened as the B0, which is nothing but the applied magnetic field increases, the localized magnetic field also increases. Magnetic field felt at the local field also increases. So the sigma or the chemical shift anisotropy is a parameter which depends on the applied magnetic field. Higher the magnetic field, higher will be the chemical shift anisotropy. That is why people say when you go for nucleus like platinum, palladium, or lead 207, or tin, if you go to higher and higher magnetic field or higher and higher frequency, you will get more and more chemical shift anisotropy. So to get a reduced chemical shift anisotropy, you need to do the NMR experiment at lower frequency or lower magnetic field. The frequency is nothing but omega is equal to gamma H0 or gamma B0, where B0 is the applied magnetic field. So once the magnetic field decreases, obviously frequency also decreases, because you know omega is equal, always people will write omega is equal to gamma B0. Omega is equal to, omega is equal to gamma B0. I think it is not writing. Omega is writing now. You see gamma B0. So gamma is nothing but the gyromagnetic ratio. B0 is the applied field. Once omega is higher, for example, if you go for 300 megahertz and if you go for 500 megahertz, 300 will be having a lower magnetic field around 7.04 Tesla, and 500 megahertz will be having a magnetic field of around 9 point something Tesla. So magnetic field is different. So the chemical shift anisotropy also will be different. It increases with increase in magnetic field. So these are the two contrasts. Dipole-dipole is independent of the magnetic field, whereas chemical shift anisotropy depends on the magnetic field. There is something called quadrupole shift, quadrupole NMR or quadrupole anisotropy. We will discuss it maybe next class. That also has a magnetic field dependence. Maybe first term is inversely proportional to the magnetic field and the second term is proportional to the magnetic field. This we will discuss in the next class. So let us move further. Yes. Another property of the dipole-dipole coupling is called, it is giving a homogeneous broadening. What do you mean by this? I have shown a spectrum here. X-axis is wavelength, nothing to do with the NMR spectrum here. And Y-axis is nothing but intensity. You can say an emission spectrum, you can say. So if you see here, homogeneous broadening means, you see broadening, there are various Gaussian components or Lorentzian components which are overlapping. In this red peak, say red is a broadened peak. The red is nothing but a homogeneous broadened peak. Black is nothing but an unbroadened. This I have given a typical example only, representative example. So homogeneous broadening means it is nothing but it will broaden homogeneously. So dipole-dipole coupling is an interaction or a coupling interaction which leads to homogeneous broadening. So this is the basic effect. Dipole-dipole coupling is, what I mentioned, is independent of the magnetic field, and also it leads to homogeneous broadening of the line shapes. So for example, if you take proton in solids, you will get like this line shape. Whatever may be the sample, if you take a proton NMR, any organic compound, or without doing proper treatment, but the NMR spectrum directly you get is like this, a broad peak. So this is a homogeneously broadened line. So here, one more property is there. See, as I mentioned in the previous class, I think second or third class, I have mentioned that dipole-dipole coupling is not a vector, but it is a tensor of rank 2. Any tensor, normally we represent in terms of a matrix. In the case of a tensor with a rank 2, we have 9 component. Rank 2 means 3 into 3 raised to n, where n is the rank. So when n is equal to 2, it is a second rank tensor. So 3 squared is nothing but 9. 9 components will be there. So the trace means if you sum all the diagonal components, we get 0. If it is a homogeneous modeling or if it is a symmetric tensor. So dipole-dipole interaction is a symmetric tensor, whereas chemical shift anisotropy is an asymmetric tensor. We have a definite value of the trace. Trace is nothing but 1 by 3 into sigma 1 1 plus sigma 2 2 plus sigma 3 3, or 1 by 3 into delta 1 1 plus delta 2 2 plus delta 3 3. So chemical shift anisotropy, we do it is a traceless. It is a traceless tensor, whereas dipolar interaction is a symmetric and a traceless tensor. Trace will be 0. Whereas the chemical shift anisotropy is an asymmetric tensor. This is the difference between the chemical shift anisotropy tensor and dipole-dipole tensor. So chemical shift anisotropy is an anisotropic interaction, whereas dipole-dipole interaction is an isotropic interaction. Isotropic broadening occurs and it is not affected by the magnetic field and it is represented by a traceless tensor. These are the 4 parameters which you keep it in mind. Chemical dipole-dipole interaction. Whereas chemical shift anisotropy, these are the two interactions which decide the line shape of the NMR patterns. The chemical shift anisotropy is nothing but it's an anisotropic interaction. It can inhomogeneously broaden the line shape. I don't know whether you remember or not. In some in the previous classes, I was showing a line shape like this. Sometimes I was showing a line shape like this. The last class I was showing for some carbon atoms, probably carbon atoms of the sp2 carbon atoms in the phenylic rings will have a line shape like this. Tin oxide, I don't know whether you remember last class, I have shown something like this one, spectrum something like this. If you take a static spectrum, it will be something like this. And sometimes you get peaks like this one. Here, sigma 11 is equal to sigma 22 or delta 11 is equal to delta 22. And sigma 33 will be different. These are isotropic, these are nothing but as symmetric chemical shifts. But in general, chemical shift is an anisotropic interaction. So we do not have, the trace does not average out to 0. There's a specific value to the trace. So tilting tensor can be diagonalized to use a tensor with the 3 principal components. That is we call as a principal axis system. So that is a principal axis system I am shown here. So this is the magnetic field and this is the principal axis, delta 11, delta 22 and delta 33. Under this condition, it can be diagonalized. So in the last class, I don't know whether you remember or not, I mentioned that simulated NMR spectra. Simulated, once you get the experimental pattern, then we try to see whether we can simulate that NMR pattern. So how to simulate that NMR pattern? Simple only, there are programs, but forget about programs. The basic principle is that the chemical shift can change the frequency, resonant frequency. If this is the operating frequency, the actual chemical shift is expressed by this type of expression, where theta and phi are the polar angles which are mentioned in this diagram. So depending upon the axis, the molecule symmetry axis, how it is oriented with respect to B0. That means the principal axis of the molecule, how it is oriented with the B0, depending upon the orientation values of theta and phi, depending upon the variation in theta and phi. For example, this is a theta and this is the phi. Of course, there's a slight change in the position here. Forget about that. This is phi angle and this is the theta angle and there is a. So because depending upon the orientation of the principal axis with respect to B0, we can have different nus and one can theoretically generate various angles and get the line shape. Only thing is you have to match with the experimental pattern, so particular value of orientation. So then you say it's a simulated pattern which matches with the experimental pattern. That is what we do in powder patterns calculation. So calculate the frequencies for a large number of orientations. You can calculate the frequencies over a large number of orientations. Orientation large number means theta and phi will be different. So that is why we calculate the large number of orientation of the interaction tensor with respect to the magnetic fields. So you can generate a symmetric pattern. So these are just some introduction regarding the dipole-dipole interaction and the chemical shift anisotropy I thought I will give because most of the time we are discussing that aspect only. So now let us go to again the NMR spectrum. So this is an NMR. See, there are materials of different types. One can be a crystalline material and another can be a glassy material. So glass, another form is vitreous. Vitreous and glass are almost same only, they are synonyms. and vitreous correspond to glass. So silica can be glass also, there can be crystalline also. What is the essential difference? In vitreous silica, there can be a short range ordering. For example, if you see a black carbon, there are having how many are there? 3 green spheres are there. So that much will show. Few angstrom there is an ordering, but beyond that there is no ordering. Whereas in crystalline, what happened? This carbon atom, this black atom is having three oxygen, and then again at a particular distance we have again black atoms. This black atom, this black atom, this. So there is an ordering is there. Their systematic variation is there in the atom position. Whereas glass there is no systematic variation, and this leads to the broadening in the NMR pattern. Sir, waiting in the lobby, it is written. Shall I let it? Sorry, I forgot. So vitreous silica versus crystalline silica is done here. So accordingly, properties also changes. So say once it is crystalline material, what happens? There are other properties. Whereas glassy material, if you see, there is brittleness comes into picture, and then a thermal expansion coefficient can vary compared to that of the crystalline material. Hardness can vary. Many of the mechanical properties can change with as you convert from amorphous to or the crystalline to glassy materials. So this probably I have also told in the last class. When in the case of silicates, what happened? We have got say SiOSi bridging oxygen atom. The moment you add sodium, one bridging oxygen atom gets converted to non-bridging oxygen atom. So in a silicon, we all know it is a tetrahedral coordination. So we have a Q4. Q4 means what? Silicon with 4 bridging oxygen and 4 silicon as next near neighbors. The moment one bridging oxygen atom gets converted into non-bridging oxygen atom, we have only 3 bridging oxygen atom. That is why Q3. So that is hardly around 8 to 9 ppm chemical shift different. So by recording NMR, you can always find out which structural unit is there in the glass and how they vary as a function of composition. This is also similar to that only. This can be done even for multiple glass composition, glass with multiple composition, in the sense that this glass is having alumina is there, boron is there, potassium is there, sodium is there, multi-component glasses. Then also you can selectively probe what is the type of the silicon structural unit present, whether it is Q2 or whether it is Q4. Q4 means 4 bridging, you see here, and Q3 means 3 bridging and 1 non-bridging. Q2 means 2 bridging, 2 non-bridging. So this can be very easily calculated, and this can be used to explain some of the parameters like thermal expansion coefficient, glass transition temperature, etc. Because you see here, the x-axis, the Q4 structural unit concentration is increasing. And y-axis is what we see, glass transition temperature is increasing. And another side of y-axis, what you see is thermal expansion coefficient increasing. So this is the axis. This curve is for thermal expansion coefficient, and this is the x-axis where you see an increase in Q4 structural unit. Once you increase in Q4 structural unit, Q4 is nothing but silicon with all 4 bridging oxygen, 1 bridging, 2 bridging, 3 bridging, 4 bridging. Here 1 is non-bridging. All remaining 3 are bridging. So this is a Q3 and this is a Q4. So here, as you increase the Q4 structural unit, you see here Q4 structural unit increasing. But what is happening? Thermal expansion coefficient systematically decreases. You see here, the fraction of Q4 is around 0.1 or 0.08. As you increase the concentration of the or fraction of the Q4 structural unit from Q4 to 0.8, the thermal expansion coefficient systematically decreases. Whereas the glass transition temperature, you see, glass transition temperature systematically increases with increase in Q4 structural units. What is the reason? A qualitative explanation is like this. Once you increase the Q4 structural unit, Q4 is nothing but all the 4 bridging oxygen atoms are connected to silicon. So they are a rigid structure. So once we have a rigid structure, then we have a lower thermal expansion coefficient because the material will not thermally expand. Because thermal expansion, if a material want to get more thermal expansion, means its network should not be rigid. It should become less and less rigid. So otherwise, if it becomes more and more rigid, then what happens? The thermal expansion coefficient will keep on decreasing. The material will not expand. The material can withstand temperature. So that is why thermal expansion coefficient decreases with increase in Q4 structural unit. On the other hand, the glass transition temperature is a phenomena that increases with increase in Q4 structural unit. Why? Because the network becomes more and more stable if you increase the Q4 structural unit. So the glass properties can be studied, or any material property can be studied by measuring the relative concentration of Q4 structural units. Here comes the importance of solid state NMR. See, with no other technique can give the information regarding the Q4 structural unit. Only silicon content mass NMR. By recording NMR only you can get this information, and then only, and with that information only you can understand the variation in the thermal expansion coefficient or glass transfer temperature. Here lies the beauty of NMR. No other technique can give this information. Sorry, let's continue. So in any glass is an important material for our Department of Atomic Energy, and as well as for other important applications. In many of the glass to metal sheets, we have feed-through materials. The thermal expansion coefficient of the feed-through material is an important aspect, because this has to match with the metallic material which are used. Because the feed-through material will be covered by either stainless steel or Inconel or whatever material. So the thermal expansion coefficient of the glass as well as the steel should match, then only it will form a very stable seal material. Otherwise, there will be inhomogeneities and seal can break and material can come out. So it is important that we need to understand the thermal expansion coefficient and correlate with respect to the structural parameters in the glass. Let us go further. Another important aspect of this silicon contained NMR is like this. See, when you make very, very big bridges, etc., people use concrete. Concrete used to make bridges and these pillars, etc. So how to study the concrete, whether it is stable, and it has to be stable not even 5 or 6 years. It has to be stable maybe 100 years, 75 years or 100 years, etc., because the bridge has to remain for a long time. So how to study whether the net structure, whether a concrete is stable or not? If you put it in water, you will not come to know, because we cannot wait all the 100 years. So what people will do, they take concrete or they take cement or they take the material and put it in water and subject high pressure and high temperature. These are called accelerated testing. Accelerated testing. What is accelerated testing or accelerated reaching? You create an environment which is destroying the material, like high pressure, high temperature, etc., so that water molecules or the material is dissolved in the water, attacks the glass, so that the glass or the concrete, so that it degrades quickly. Once it degrades quickly, maybe within a day, whatever may be happening over 100 years may be taking place over within few days or maybe in a month's time, then we can understand, okay, these are the degradations taking place with the material, and then we can correlate what will happen after 100 years. Because nobody can measure any property change after 100 years, because we cannot wait till that time. The same thing is also valid for the waste immobilized, radioactive waste immobilized glasses, because we want to have the glass should be stable more than 100 years. So we do not know what will happen after 100 years. We cannot predict that. To do that, we need to do accelerated testing. So create an environment which is destroying the material, which can destruct or which can create problems to the material, so that the material can decay or the material can undergo leaching. So this type of experiment, NMR, will become useful, because by doing that, you will be able to find out what is the structural changes taking place. In this regard, we have also recorded some glassy material we have subjected to accelerated leaching. Suppose this glass is a borosilicate glass which can be used for the waste immobilization. So we want to know how it will happen after 50 years, or what will happen to the structure after 70 years, 75 years. So we have also recorded the glass, taken the glass samples and subjected it to accelerated leaching conditions. We have put it in an autoclave, added a lot of alkali, added a lot of water, then subjected to high pressure at a temperature of 200 degrees centigrade. So what happened under this condition, the glass is found to get decomposed. You see, the glass is getting destroyed. You can see one species which is getting generated, called an aluminosilicate phase, is getting generated from the glass. Of course, beyond some concentration, XRD will tell, but at low concentration, up to this 192 hours leached sample, we can see the XRD will give the information. But at low hours or low duration leached sample will not give the proper information by XRD. XRD technique may not be giving the proper information. Here, NMR can very well give the structural units which are getting generated. So an aluminosilicate crystalline phase is getting generated in these glasses, and once the crystalline phases get generated containing sodium, the sodium can leach out in the solution and create proper activity, migrations, etc. So this is one important information which we get from silicon-29 mass NMR. Silicon mass stands for the magic angle spinning. Similarly, you can also do silicon NMR of different crystalline modification. You see, silicon carbide and alpha silicon carbide and beta silicon carbides are very widely used for making furnaces, furnace tubes, etc. So here, this beta silicon carbide is having a cubic structure, diamond type of structure or a single blend type of structure. Whenever there is a cubic structure, you see here, there is only a single signal is there and the line shapes are relatively sharp. Of course, for other samples also relatively sharp, but only one type of silicon environment is present in beta silicon carbide. Whereas its alpha form is at least 3 different crystallographically different silicon structural units which have been obtained by silicon-29 mass NMR. In fact, X-ray, if you do a very careful X-ray diffraction studies, we can also fit this silicon carbide structure into 3 different silicon structural units. But the moment you convert crystalline silicon carbide to amorphous silicon carbide, then what happens? We will get, it is neither cubic nor hexagonal, and we get a broad distorted silicon peak, as can be seen from this NMR spectrum, which is at a chemical shift value of -12. So silicon next near neighbor, 12 to 3 different configurations are possible. So hope it is clear. Similarly, different crystallographic forms are Si3N4. Si3N4 is also used as a very hard material, similar to that of diamond. So it has also exists in alpha and beta structure. So beta structure is somewhat cubic structure. You can see a single peak, whereas the alpha structure we more than one type of silicon structural units are there. This is very clearly seen from both this NMR pattern. This I am giving you to get a feel of how the silicon NMR can be used to interpret the silicon structural unit present in Si3N4. Similarly, if you see, as I mentioned in the first or second class, as the coordination number increases, the chemical shift decreases. Decreases means chemical shift become more and more negative, means shielding will increase. For example, if you take tetrahedral silicon with the silicon nitrogen linkages, silicon having 4 nitrogen as near neighbors, we will get a chemical shift of -50. But if you go for a silicon structural unit or a silicon nitride system with the 6 nitrogen as near neighbors, what you get is a more chemical shift, more negative value of chemical shift. Means shielding is more. As the coordination number increases, shielding increases. Why this happens? Because as the coordination number increases, the bonds increases. Once the number of bonds increases, the electron density around that atom increases. And once the electron density increases, shielding becomes more. And the more shielding means we have lower and lower chemical shift value. That is why in a cubic Si3N4 we have a cubic tetrahedral silicon also, octahedral silicon also, and the tetrahedral silicon comes around -50 ppm and octahedral comes around -25 ppm. So these are the things which we can use. Solid state NMR can be used to identify. When you have a silicon mixture of silicon oxides and silicon nitride, one can very well see which is a silicon nitride peak due to tetrahedral silicon and silicon nitride peak due to octahedral. So these are simple identification information which you can get from 1D mass NMR technique. So another thing which I am going to tell is a very important aspect. This is NMR. This is called a cross polarization magic angle spinning NMR experiment. So far, I have only mentioned about magic angle spinning NMR. MAS stands for magic angle spinning. We run higher and higher spinning speed and we get the NMR signal. But now there's a technique. Now means it is well known for the last 20-30 years. That technique is known as cross polarization magic angle spinning NMR, CP-MAS. Short form is CP-MAS. What do you mean by cross polarization? Cross polarization is a terminology only. Cross polarization means transfer the polarization from one nuclei to the another nuclei. For example, if you take proton, which is an abundant nucleus, highly abundant nucleus, transfer the population from proton to carbon-13. In other words, transfer the population or polarization from one nuclei to the another. So this is called a cross polarization. Cross means it is not transferring from one proton to another proton. It is doing transferring proton from 1H nucleus to the carbon-13 nucleus. Carbon-13 is less abundant. So by transferring the population, you can get improved signal-to-noise ratio of carbon-13 NMR. Because carbon-13 NMR is carbon-13 abundance is very, very poor. So we get poor signal-to-noise ratio from carbon-13 NMR. So how to improve carbon-13 NMR signal? Because we need to get a good quality carbon-13 signal, because proton NMR alone will not give all the structural information of organic compounds. So we need to get the carbon-13 information also. So how to get that is by a process known as cross-polarization. So cross-polarization is nothing but transferring the population from one nuclei to the another, one abundant nucleus to the less abundant nucleus. So the moment you transfer polarization or population, you require a medium. Just like that, you can vacuum, you cannot transfer. Some sort of a interaction or some sort of a coupling is required. Without coupling, you cannot transfer the population. So some sort of a coupling is required, and this coupling is achieved through a phenomenon called dipole-dipole coupling. So this is the one advantage of dipole-dipole coupling. So in all the previous slide, we try to do mass NMR and try to get rid of the dipole-dipole coupling. Here I am saying that dipole-dipole coupling is a gift for us. It is a gift given by God, because by do dipole-dipole coupling, we can transfer the population from proton to carbon-13. But can you see the proton magnetization is different? You see the level difference? Because omega, always I am repeating this word, omega is equal to gamma H0. Omega is equal to gamma H0. So H0 is the applied field, gamma is a zero magnetic ratio of the nucleus. So gamma is different for proton and gamma is different for carbon-13. So they are different, so their Lamarck frequencies are different. So once the frequencies are different, how you can transfer the population? Is it not? It is not possible to transfer. For example, if two buses are going with different velocity or different speed, the person from one bus cannot be moved to the other bus. But if two buses are moving in the same speed, and if their doors are closed, one person can move from one bus to the another, although it is very, very dangerous. But if they are moving at different speeds, it is not possible to jump from one bus to another bus. Similarly, the Lamarck frequency of proton is different from that of carbon-13. Then how we will have a polarization transfer or the population transfer? So this is what I will be discussing in the further slides. So the cross polarization can be achieved by suitable pulse programs or by applying suitable pulses. By the help of suitable pulses, we can affect the transfer of population from proton to carbon-13. So that is what we are discussing in this slide. Next slides. So why cross polarization is required? Because we want to enhance the signal to noise ratio from carbon-13, nitrogen-50, and the silicon-29. Because carbon-13 is less abundant. If you want to get good signal noise ratio, we need to have some sort of a polarization transfer from proton. Invariably, in all organic compounds, carbon many times associated with hydrogen. So we are lucky that we have an abundant species like hydrogen which is very close to that of carbon. So with that dipole-dipole interaction, if it is away, hydrogen is away from carbon, then we cannot do, because dipole-dipole interaction decreases with the increase in distance. In fact, it is inversely proportional to the cube of the distance. So as the distance increases, we cannot do. But if there is a proton at the proximity of carbon, then the population of the proton can be transferred to carbon-13 by a process known as cross-polarization. The same thing also can be converted to do it for nitrogen-15, and nitrogen-15 as well as silicon-29, because their abundance are very small. So if hydrogen is attached with them, then we can transfer the population proton to the nitrogen or carbon-13 or silicon-29. So listen carefully. This is I will explain to you how this phenomenon is occurring. So you might have learned in a previous solution NMR classes that modern NMR spectroscopy is based on pulses, by applying pulses. You have 90-degree pulse, you have 180-degree pulse. By applying suitable pulses, you can get good signal noise ratio. So here also we apply pulse in a manner to get polarization transfer from proton to carbon 13. So first you see here I am applying a 90-degree pulse. Correct? No? I am applying a 90-degree pulse. If you apply a pulse, 90-degree pulse around the x-axis, you know the magnetization will come on the y-axis. It is mutually perpendicular. We can express it as a cross product. So if you apply a pulse along the x-axis 90 degree, you get the magnetization in the y-axis. Which magnetization in the y-axis? The magnetization of proton is in the y-axis. Now, I apply a magnetic field along the y-axis so that the magnetization which has come to the y-axis, the proton magnetization which has come to the y-axis remains there with the applied magnetic field. Okay. Then what I am doing? Then I am applying another pulse to carbon 13. Another pulse called a spin locking pulse or a mixing pulse to carbon 13. I am not applying a 90-degree pulse. I am applying a contact pulse. Contact pulse also is similar, it's a pulse only. Contact pulse is a pulse only, but it is not a 90-degree pulse. Its width is higher. It is there for a long time. So a contact pulse is applied along the C13 axis so that the C13 magnetization is maintained by this pulse. So in other words, we are contacting proton with the carbon 13. So whenever there is a contact pulse on carbon 13 as well as the hydrogen proton, then what happens? Their frequencies become same and the population transfer from proton to carbon 13, and that is why we see an enhancement in the signal. Being made a statement, the frequency become equal. You may think that how the frequency become equal, because just now in the previous slide I told omega is equal to gamma h0, gammas are different, so h0 is gammas are different for different nucleus, so h0 is same, so gamma has to be different. Then how you can make the omega or the frequency same for both carbon 13 and proton? You cannot make the frequency same in laboratory frame. The frequencies are made same in the rotating frame. As you might have learned, or it might have been discussed in your previous class, something called a laboratory frame, but that is nothing but the magnet is rotating or a frequency under at the frequency of Lamarck frequency. But there is something called a rotating frame. Hope you might have understood that. If you have any query regarding the rotating frame, you can ask, but for the time being, I will continue with the rotating frame. You can go through your previous notes and find out what is the difference between a laboratory frame and a rotating frame. For the time being, I take it granted that you might have already gone through these concepts of laboratory frame and rotating frame. In case any doubt, you can mail me. I can discuss it also. Maybe next class also I can discuss. In a rotating frame, let us see we have two systems, which is carbon 13 and hydrogen, or proton. Let us say proton and carbon 13. In a rotating frame, applied magnetic field doesn't matter. Whatever may be the applied magnetic field or the frequency. For example, you have a 300 megahertz machine, you have a 500 megahertz machine. The rotating frame is assumed that it is also rotating with respect to 300 megahertz or with a frequency of 500 megahertz. The rotating frame is also undergoing a frequency or undergoing a rotation with a frequency of the spinning frequency, which is nothing but the Lamarck frequency of the proton. So if you say 300 megahertz, proton will be having a frequency of 300 megahertz. The rotating frame also rotating at a frequency of 300 megahertz. So in the rotating frame, it as if there is no magnetic field applied to proton. Similarly, in the rotating frame, as if there is no magnetic field applied to carbon 13. Hope it is clear to you. So in the rotating frame, the effect of magnetic field is negligible. There is no effect of magnetic field. Now, if you apply a suitable contact pulse of a suitable magnitude on H1 and a suitable magnitude on C13, there is a possibility that the frequency of C13 and the frequency of proton can come to a same value. Very interesting phenomenon. So here, frequency of proton and frequency of frequency of proton and frequency of carbon-13 can come to a same value. How? By applying a spin locking pulse. By applying a spin locking pulse, what you are doing is applying a magnetic field along the rotating frame, and this rotating frame, in the rotating frame, the nuclei does not depend upon the applied magnetic field. So magnetic field created by the spin locking pulse only predominates. So if you adjust the spin locking pulse in such a way that the frequency of carbon-13 and frequency of protons are same, then what happens? There's a communication between carbon-13 and proton. Or the carbon-13 can interact with proton, or proton can interact with carbon-13. Once proton interact with carbon-13, what happens? There is a population transfer from H1 to carbon-13. So that is why we see a peak. Peak means these are all peaks which are formed called FID, free induction decay. This can be Fourier transformed into spectrum. Hope it is clear to you. So this method is called cross polarization. Cross polarization from proton nucleus to carbon. It's a very, very important concept. The most of the NMR, 70% of the NMR works on cross polarization only. I'll be talking whatever organic compounds, carbon-13 and hydrogen is there, cross polarization is there. Similarly, in many of the hydrosilica, where there is SiOH group, here in SiOH group, what is the problem? Hydrogen is not close to silicon. It is far away because in between one oxygen is also coming. In carbon, many of the carbon compounds, hydrogen and carbon are nearby. So dipole-dipole interaction depends upon the near neighbor distance. Once it is smaller, the dipole-dipole medium is there. This due to the dipole-dipole interaction only, this population transfer is taking place. So if there is no dipole-dipole interaction, then we will not get this type of cross polarization. So that is why cross polarization is a very, very important aspects in solid state NMR spectroscopy. So you transfer the population from hydrogen to carbon-13. That is why most of the organic compounds, some organic compound we can do NMR, solid state NMR only because of this cross polarization phenomenon. So in cross polarization phenomena, it's a double resonance technique, not a single resonance, because two resonances are there. One is carbon-13 and another is proton. So first you apply proton, 90-degree pulse, bring the magnetization to y-axis and lock that magnetization by applying a pulse, locking pulse. Same thing you do for carbon-13 also. By adjusting the magnetic field in the locking pulse, that is nothing but the B1, we can have the same omega-1 for carbon-13 also and hydrogen also. In this process, once the frequencies become same, population can be transferred from proton to carbon-13 and we see a signal here. So as I mentioned, after 90-degree pulse along x-axis, the magnetization come to y-axis. See magnetization to y-axis. Now decoupling. I think what happened? Okay, that I will come back to it later. Now second, I think in between some slides. Second, first after this one, so after 90-degree pulse along x-axis, magnetization come to y-axis. You see here y-axis. Now what is the second step? In second step, immediately the phase of the radio frequency is shifted to y-axis by turning 90-degree and continue to radiate. So is it clear to you? So what happened? First, I apply the pulse along the 90-degree x-axis and the magnetization come to y-axis. The moment the magnetization come to y-axis, immediately the phase of the radio frequency is shifted to y-axis by turning 90-degree and continue to radiate. We are not switching up. So the magnetization is locked in the y-axis. You see the proton magnetization is locked in the y-axis. It has gone to its x-axis first. Then by changing the RF field, we have locked it to y-axis. Now, RF field is H1 is larger than the local field based on dipole-dipole interaction, and the effect of the external magnetic field is eliminated. That I just now mentioned. The H1 field is larger than the local field based on the dipole-dipole interaction, because the H1 is nothing but the field which we apply, correct now, by applying in the form of a pulse. So that H1 field remains here. H0 is nothing but the applied magnetic field. H1 is nothing but the pulse field coming from the 90-degree pulse, because it is modulated with the carrier wave. So H1 is the H1. RF field H1 is larger than the local field based on the dipolar interaction, and the effect of the external field is very, very high. It is eliminated in rotating frame, that we know. So this process is called a spin lock. So this process is called a spin lock. So the magnetization is locked. Magnetization is locked. Now what happened? Now what I will do? Now if you see a little bit mathematics of that, the Curie's equation is there. Curie's equation says that what happened? The magnetization is given by this type of expression. Magnetization is expressed by this type of inversion. This is nothing but M Z. Normally we see the Z component only. Z component of the I magnetization. So I is nothing but proton, and S is nothing but spin 13. Carbon 13 or spin half nucleus. For example, I mentioned here also. I is nothing but proton and S is nothing but carbon 13. So same is valid here. First, let us say what happened to the magnetization of I in the Z axis. So that is given by this expression where H0 is the applied magnetic field, which is sometimes written as Bs, and TLI is the lattice temperature, and 3K is nothing but the Boltzmann constant. TA is nothing but the lattice or the laboratory temperature. Na is the number of I spin, and I is the spin value. I is equal to half here. So magnetization spins in the rotating frame. In the rotating frame, what happened? Rotating frame, there is no applied magnetic field H0. We have only got H1. So that is why H1 comes here. So MRI means it is in the rotating frame. Here it is in the laboratory frame. In the laboratory frame, which depends upon the applied field, but in the rotating frame, what happens? We do not have H0. Why H0 is not there? Because we are moving at a frequency which corresponds to the H0. So if you see that since we are rotating also, in the rotating frame, this H0 effect will not be there. So that whatever applied frequency to the pulse only will be there. So that is what I have written here. It is nothing but H1, which is nothing but the applied magnetic field which is coming through the pulse, and this TRI is nothing but the rotating frame temperature. TL is nothing but the lattice temperature or the laboratory frame temperature, and TR is nothing but the rotating frame temperature. But I have already mentioned that in rotating frame, no effect of the applied magnetic field. So M is a I is nothing but MRI. M is a I is nothing but MRI. So if you equate this one term, what is nothing but the rotating frame temperature of I is given by TL, which is nothing but the laboratory frame temperature of I into H1I divided by H0. H1I is nothing but coming from the applied, the radio frequency 90-degree pulse magnetic field, or which is nothing but the applied, not the applied frequency magnetic field, the 90-degree pulse magnetic field H1.
Wait. Someone is waiting.
Waiting in the laboratory.
Last moment.
So what happens H1? If you see here now, I think I will within 2 minutes. I will. The moment I explain the concept, I will finish. So H1. H1 is nothing but the magnetic field coming from the 90-degree pulse applied 90-degree pulse, and H0 is nothing but the static of the applied magnetic field. So you know H0 is nothing but HL only, lattice or laboratory frame only, that is almost 10 raised to 4 gas, whereas H1 is nothing but 10 gas. So what you see is nothing but the rotating frame temperature is 10 raised to minus 3 times lower than that of the laboratory frame temperature. So the spin temperature of the rotating frame is lower than the laboratory frame of pi. That is what the important concept here. So there is no effective actual reduction in temperature. The effective field is less. That is what I want to convey. So this concept, now you understood, you are in a rotating frame, and in the rotating frame, spin temperature of rotating frame is lower than the laboratory frame. So 2-3 things I have told. First is the magnetization. I come to the y axis, and then I have locked the magnetization on the y axis. Then I have talked about the spin temperature. And I have mentioned that the spin temperature of the rotating frame is much lesser. Now the third step involved is a spin, which is nothing but the less sensitive spin, like carbon 13 is irradiated with a radio frequency of H1. Yes. So now you do it in such a way, apply the H1 yes, or the magnetic field of the radio frequency of the S nucleus in such a way that gamma I is nothing but the zero-magnetic ratio of proton multiplied by the H1 radio frequency of the proton nucleus will become equal to that of the product of the gamma S, which is nothing but the zero-magnetic ratio of S nucleus multiplied by the H1 field applied for the S nucleus. So if you satisfy this, then we tell as Hartmann-Hahn condition is achieved. So under Hartmann-Hahn condition, the omega I, which is the frequency of I nucleus, which is nothing but the proton, will become frequency of the S nucleus, and there is a proper communication between omega I and omega S possible, and the population can be transferred from I to S. So this is what happening in cross polarization. So third step is the most important step. You apply a radio frequency at the S nucleus, and in such a way that the product of the gamma I, zero-magnetic ratio of I, and radio frequency applied for the H1 proton nucleus become equal to the product of the gamma zero-magnetic ratio of the carbon-13 and the radio frequency applied for the S nucleus. Once it becomes equal, this is equal only in the rotating frame, and once it becomes equal, then there is a population transfer occurs, and we get beautiful signal in the S nucleus or the carbon-13 nucleus. Hope it is, you have to understand, you have to think about this further. So this is the way we get polarization transfer from proton to. With this, I think I will stop here for the time being. Think about it, and then probably once again I will brief you in the next class regarding the carbon-13, maybe a little bit quickly, and then move further. So I will just show you some examples of carbon-13 NMR, CP-mass NMR, so that you will get a better understanding of this in the next class. So thank you very much, and please feel free to ask questions. I'll be happy to answer any questions. So please feel free to ask questions. Any questions have come? Can we see any question? Somnath.
What is that?
Welcome to.
That is. Any question? Anyone? No.
Please feel free to ask questions.
Yes, Darshan, this temperature, that radio frequency temperature, we're correlating that. Why I should tell that as a temperature means physical meaning of that.
Physical meaning is the proton temperature is slightly higher compared to carbon-13.
That is actually frequency.
Actually, magnetic field is higher because gamma is higher. So proton temperature is higher. So whenever temperature is higher, from higher temperature to lower temperature, population can be. Suppose you have a hot body and cold body, keep together.
Okay.
Temperature can go from hot body to cold body.
Okay, that's why you are thinking.
So similarly, carbon-13 and proton is high temperature species. High temperature is not there because of the population or the magnetic field, which is high temperature. So and it is in dipole coupled with the carbon-13. So they are close to each other. So the heat can go from proton to carbon-13. Heat means population or polarization can go from proton to carbon-13, and as a result, sensitivity improves. This probably I will tell next class. So that this has coming only, that is all.
Yeah.
So any more questions? Please feel. Oh, it's already no more questions. Okay. So next Wednesday there is no class. Next class is on Friday, which is I think it is on 21st. I think if I remember correctly, because correct, na? 19th is Wednesday and 21st is the next class. Friday. Please come
next Friday.
Next Friday, please come. Very important class that is, because we are going to discuss a lot of C30 and CP-mass NMR spectrum. How important the technique is.
Why you just write there? Next class is on.
Next class is on. I forgot.
21st.
Class is on 21st July, Friday, 3:30 to 4:30. Please join. So very important aspect that I am going to discuss.
2023 at 3:30.
That must be my 8th lecture.
Good. Okay. Okay.
Okay, thank you very much.
YouTube.
Why is it showing this one?
Delay.
Delay, okay.
Oh,